In this video, I'd like to go over a few examples of situations that might get you hung up on the assignments that you have to do for this course in Lesson 404. So let's start with the first example. For this one, a particle is moving along the x-axis so that its position at t greater than or equal to 0 is given by this position function. Find the acceleration of the particle when the velocity is first 0. So a couple things here. We're going to eventually need to find an acceleration. So the final answer is a numerical value. We'll have to plug something into the acceleration function. And that number that we're plugging in is when the velocity is first 0, which gives me an indication that there's more than one 0 since they ask you for the first 0. So either way, we need to find the first derivative to get the velocity and then the second derivative to get the acceleration. Okay, so our s of t function is the position. To get the derivative, we need to use the product rule here because there's two functions there. There's a t squared function and then the exponential function. So the product rule is going to look like this. And I always remembered it as the first term times the derivative of the second plus the second term times the derivative of the first. And that's just the way I've learned it. Like I learned it that way years and years ago when I learned calculus. I know StudyForge uses the like f prime and fg prime in the formula, so it's up to you how you do it. Either way, the addition makes it so you can do it either order. But notice when we took the derivative of the e function, you need the chain rule because e is itself, when you take the derivative of e is itself untouched and then times by the derivative of its exponent. So this is the first times the derivative of the second plus the second times the derivative of the first, which is just 2t. Okay, let me just clean that up a little bit. Because of all the multiplication going on here, you can just rewrite it. I put the 2 in the front, the t squared, and then the e, and the same thing, I just put the 2t in the front here. So just made that look a little nicer. And now while we have the velocity equation, we might as well set it equal to 0 and solve it so we can get where it equals 0 the first time. So now this situation, this is kind of icky. What do you do when you have problems that look like this and you have t's, you have a t squared, you have a t here, you have a t in the exponent? This is not like your typical like quadratic situation because of the e, but you can still factor it. Take out the common terms, which actually happen to be the 2 and the e for both terms. They both have that as part of each term, so you can factor it out. And then you're left with two pieces that are being multiplied. This is where you use the zero product property. This is something that you did when you factored quadratics, like, in Algebra 2. Anytime you have two things being multiplied, if you set each one equal to 0, then that means that you'll find the value that will cause the whole thing to equal 0. Because if you find the value that makes this equal to 0, then the whole thing equals 0 because of the multiplication between them. So that's the next step. Set them both equal to 0, solve for t. So the situation now is that this thing has no solution. That will never ever equal 0, ever. And that's just because it's an exponential function. Exponential equations never equal 0. It doesn't even matter that it's an e. It could be any base. They never equal 0, ever. So this one will have no solution, and you can divide by 2 and take it on to the next step. But either way, it doesn't have a solution just because it's an exponential function. Exponential functions never equal 0, ever. This is like 2.7-ish. So then e squared is like 7 something. Just keeps getting bigger and bigger. If you go backwards with negatives, it just puts it in the denominator. So this actually gets smaller going this way. But again, it'll never, ever, ever equal 0, ever. So this has no solution. This one, however, we can factor. That one's a quadratic. So divide this one by 2. We're going to get no solution here. We can ignore this one. This one, we have two solutions. We have t equals 0 from this guy, t equals -1. So now those are our two solutions. We need to find when the velocity is first 0. That's going to be at t equals -1, because that's, if you read it from left to right, -1 happened first. So now let's go back to the directions. The question wants us to find the acceleration when the velocity is first zero. So we know when that is. We know that t equals -1 is when the velocity first zero. We need to find the acceleration at that time. So let's do the acceleration equation. So here's our velocity that we found a while ago. We now have to find the acceleration. Now this is ugly because not only are there two terms here, but for each term we have to use the product rule for both. Product rule for both. So here's the first piece and the second piece, and then that's just one product rule situation. And then same thing here. Here's the first piece, the second piece. There's another product rule situation. So this is icky, but it's doable. Or you could do this and make it one product. Check that out. So either way, this one's easier though because now it's just one product. So we have our first times the derivative of the second. So that would be the derivative of this piece. And then plus the second times the derivative of the first. And the derivative of the first, the 2 just kind of hangs out. The e is itself untouched, and then times the derivative of the exponent, which is another 2. So this was a lot better. By factoring it, we didn't have to do the product rule twice. So kind of look out for that. Okay, let's simplify this a little bit. This piece I didn't touch. You don't have to simplify very much. Don't go crazy with the simplifying because, again, we're going to be plugging in a number here, so don't go crazy. I just kind of put this piece in the front. I multiplied those two 2's and gave it a 4, and then put the e in the front. You don't need to distribute though. There's no point in that because the next step is plugging in that -1. And now once you simplify all this, you end up with a -1 right here. This turns into a 0, so this whole thing goes away. And we can get rid of that second term. We're just left with -2e to the -2 power. And then final answer can look like that if you want to put that negative exponent in the bottom. So we could have done that product rule twice up here and still got the same information, same answer. So sometimes take a look and see if you can factor it out and make one product out of it. Either way though, you'll still get the same place. Okay, next one. The position of a particle on the x-axis at time t greater than 0 is our s of t function here, where t is measured in seconds, the position is measured in feet. What's the average velocity of the particle from the natural log of 2 to the natural log of 3? Okay, so first of all, students get this mixed up all the time for some reason. Here's our position function. This is just a random one, not necessarily this picture here. But our position function looks like, some kind of function. The average velocity comes from 2 points on the position function. It's an average rate of change. It's the slope formula. It's the slope of a line between 2 points on the position graph. The average velocity. The instantaneous velocity is the slope at 1 point on the position graph. So we are dealing with position function when we find average velocity or instantaneous velocity. It just depends on which formula you're using. Instantaneous is the derivative at 1 point. Average is the slope formula between 2 points. So when you do this problem, you don't need to take the derivative. They just want average velocity. So you take the position function and use the slope formula. Done. Looks like this. Take the position function, which is s, plug in the coordinates, which is, these are going to be my x coordinates, and you plug them into this function here to find your y coordinates. So it's e to the power of 3 times the natural log of 3 minus e to the power of 3 times the natural log of 2. So before you go any further though, we need to simplify. Remember the 3's are really the exponents. This is property of logs. And then those e's and natural logs cancel. So the numerator is 27 minus 8. The reasoning is, let's just look at this one for a minute. This is going to equal 8. That question mark is an 8. And the reason why is because you can take an exponential function, rewrite it as a log, because logs and exponent functions, they undo each other. They're inverses. So it's just like squares and square roots, cubes and cube roots, things like that. They undo each other. So we can take this function here, or this expression, and rewrite it as a log. And then the log is going to have the base of e, because this is the base of the exponent. The base of the exponent is the base of the log. The exponent is actually what the log is equal to. So you can rewrite this where it's a log with the base of e, and the exponent is what the log is equal to. And then this piece is actually the argument of the log. And now log base e, this is really kindergarten way of writing the natural log. So instead of log base e, it's really ln. It just has its own symbol. And if you just look at that equation, the equal sign says those are equal. So that question mark has to be an 8. So from the very beginning, I said this question mark was an 8. It's because the e and the natural log undo each other, and you're just left with the exponent. That's what the exponent is equal to. So these are gone. That's a 27 minus 8 at the top. And honestly, there's not much else you can do besides use another property of log here. When you have subtraction between two logs, it's really the division of the arguments. But that's really it. That's as far as you can go besides using your calculator.